This is Dr. Dave Matzlack talking about reciprocity.com, the sharing economy proofreading platform that I am trying to build. And today I wanted to geek out. This is where I can nerd out in science. And this series is called Nerd Out Wednesdays, and I'm going to talk to you about different words in science. This is what I'm doing for the last little while. So every Wednesday I put out a different word that you might hear scientists talk about. And the one that I'm going to talk about today is regression, because I think this is really important. Regression is actually referred to as the workhorse of most scientists. Now, I'm going to go into what exactly is regression, then I'm going to go into maybe some possible limitations, probably just some very small limitations of that, and then get into why it is so important, what's going to become more important in science and in society as we start moving forward with this. All right, so what is regression? Regression is simply a technique that we use to estimate a world of very, very messy data. So the world is extremely messy. This is called stochasticity for those of you who are interested in that. Basically, it just means that the world cannot be repeated over and over and over again. Every single time that you take a measurement, every time that you try to measure something and you do that repeatedly, you are going to get different estimates. You're going to get different observations of that particular phenomenon. It changes every single time. Now, this could be a really fun experiment if you want to try to do this. Just go and measure your weight every single minute for the next 2 hours and see what happens. Get a digital scale and try to measure your weight for the next couple of hours. You're going to see, probably what you're going to see is your weight's going to fluctuate every single time that you step on the scale. It's going to be slightly different. Sometimes it's going to be one weight and other times it's going to be another weight. And sometimes what's going to happen, particularly if you measure over a series of a couple of hours, you're going to see probably some sort of trends. It's going to go probably down if you haven't eaten anything. Maybe it's going to go up if you eat something. There's going to be changes. There's always changes whenever you measure something. It is so hard to measure any particular thing. And weight is a really easy thing to measure. Imagine trying to measure something like love. How difficult is that to measure something like love or caringness or hatred? Things like that are really, really difficult to measure. And if you think about it, that's only across a particular individual. If you're trying to measure this over an individual, that is easy to measure, but try to measure on a mass scale. So now you have to get everybody, so coming back to the weight example, getting them to measure their weight every single time you ask them to measure something. You can go home and say, measure your weight and come back tomorrow and see what happens. You ask 100 different people. They're all going to have different scales at home. The scales are going to be of different accuracy. They're going to be measuring, maybe some of them are going to be measuring their weight when they have their shoes on. Maybe some of them are not going to have any shoes on. Maybe some of them are going to be measuring their weight in the evening. Some of them are going to be measuring their weight in the morning. There's going to be all this different variance. It's just going to be really hard to measure this. So no matter how much you try to measure and how much you try to make it sort of standard and simple as possible, you cannot get the same measurement. You cannot get the same observation over and over and over again. It's going to be really difficult. There's going to be lots and lots of variability. So in this case, there's a really cool invention that mathematicians found that we use as scientists. We use this repeatedly into understanding the world. It's called regression. And sometimes we use, probably the most common one that most people use is ordinary least squares regression. And that just basically means it's the simplest one. This is the thing. And there's a lot of different assumptions. I'm not going to get into those because that's too much for today. But there's a lot of different assumptions that it does make that limit the usefulness of ordinary least squares regression, but it is also the most general one these assumptions can be generalized across, or this technique can be generalized across many different areas. And that's what we're trying to do as scientists. We're trying to create something that is useful across many different domains, and it is going to be the most useful sort of technique across all the domains in science. So for example, it's used in my field in organizational theory, heavily used in that field. It's used in psychology. It's used in all of the social sciences. I used it in engineering. It's used in biology. It's just used everywhere, because what we're trying to do is estimate the relationship between the independent variable and the dependent variable, and we're trying to estimate how those things covary over time. And that's really what we're interested in, is looking at how those covary. So if your weight goes up, does that mean intelligence goes up? Or because you ate a lot one day, does that make your weight go up? Or all of these different factors, maybe on sunny days we eat more or something like that. That's what we're trying to look at, is the relationship between two or more variables. Generally, I'm going to simplify things and just talk about two variables or two things that we're interested in, because that's what we try to do, is explain different relationships. Scientists try to explain different relationships between this and that. That's all we're trying to do. That's the basics of what we're trying to do. And the best way that we can do this, and this is the really cool, fun thing, if you measure many of this, right, you continuously measure many of this and measure many of that at the same time, you're going to get pairs of observations. You're going to get maybe at one moment for one person, you're going to get a measurement of their weight, and as well as a measurement of the amount of sunshine outside. And you do that across many different people until you have a collection of pairs of observations between the amount of somebody ate and the amount of sunshine that's outside. And you have different observations for each individual person. And then once you have that, what we try to do is we throw it into a regression. And what a regression does, it estimates the best fit relationship between this and that. So what does that mean? Basically, what it's looking at is the average relationship between how much this fluctuates and that fluctuates, and we're trying to get an average. You can look at the previous video from last Wednesday where I talked about the average effect, and that's really what we're trying to get at, is how much this goes up on average, how much this goes up, how much is that going to go up? Or if this goes up, how much is that going to go down? And that's all we're trying to get at with regression. That's the simplest way to explain it. And there is a technique, and what we're trying to do is we're trying to average out what's called the errors between each observation, and we're trying to get the minimum amount of error between each observation. And it's it's just a fancy technique where we're trying to get that minimum amount of error over time. And we get different things in that regression relationship when you run it. It's basically a set of mathematical equations where we get that. I'm not going to get into any of that because that is not the role of this video. But you get two different, or maybe a couple of different estimates, probably some that are really important. One of them is going to be a measure of what's called the intercept. That means what is the average amount of that is sort of fluctuates, or the average amount of sunshine that there is in any given day because I'm in Florida, the average amount in Florida. So that is what we're trying to look at, the average amount of sunshine in Florida. That is the intercept. That's all it is. And then you get something what's called the slope. And sometimes we refer to those as the coefficient between this and that. That's all it is. The slope measures how much, if this goes up by this much, how much is that going to go up? And it's measuring that relationship, just that slope of that relationship, so you can have a better understanding of how much this goes up, how much does that go up, or how much this goes up, how much that goes up, down. And that is all we're trying to measure with that particular slope or coefficient. We will refer to coefficients. Then the other thing that's really important, what we're trying to always look at, is because there's all this random noise in the world and it's fluctuating repeatedly and we can't get sort of a good estimate of what's going on, what we're trying to do is get a estimate of the noise that's out there. We want to rule out the amount of noise as possible, and we're trying to get at what's called a statistical significant relationship. And that statistical significant relationship, we get an estimate of how much sort of error there is in estimating the coefficient or the slope between this and that. And that's really what we're getting at. Sometimes you might hear people talk about the p-value. I'm not going to get into that. But then, so what's really cool is you get one more thing that's so interesting with a regression correlation or regression estimation. Ordinary least squares regression, sometimes it's referred to as OLS. You might hear that as well. What you do get is what's called the how much variance explained you get. So basically, all you're trying to do is measure, because the world is so noisy, we're trying to get an estimate of how much the regression coefficient and that intercept, how much does that explain of this going up and that going up. And we get often in science and most scientists, if you're explaining about 10% of what's going on, so meaning that there's a lot more noise going on and things are fluctuating. 90% of the noise that's in that data set, noise within those observations, are just simply noise. You can't explain it, but there is 10% of that can be explained with this regression or with this equation that we get. That is amazing. That's what we're trying to get, is we're trying to explain as much of the relationship as much as possible. And there's different techniques and stuff like that to explain more. So I'm not going to go too much more into that because this is kind of in the weeds as much as I would like to go. Although I wanted to point out that there is a lot of limitations with doing regression, OLS regression, that are they're pretty reasonable, right? So the technique is actually designed to be very, very reasonable. It's trying to be generalized, as I mentioned before. Excuse me. So it's very, very generalizable across many different areas. But that also means, because it's very generalizable, it makes a lot of assumptions along the way that don't necessarily fit all circumstances. So there are different techniques for each circumstance out there. And you can look at all these kind of crazy different techniques that are basically derivatives or the same thing as the OLS regression, but they're slightly different in one way compared to another way. And they're all trying to basically reduce the amount of or calculate the estimate between how much this goes up and that goes up at the same time. So that's all I wanted to say with that particular thing. Oh, one more thing I wanted to say, I forgot, is that what's really important is to point out that that correlation or that the covariance estimate that you get, that slope estimates that you get, or the coefficient that you get, that doesn't provide any causal proof. So that is the important thing to point out. And in science, it's really hard to get proof of anything. In fact, it's impossible to get proof of anything. What we're trying to do is just trying to rule out as many things as much as possible. And in this circumstance, the statistical technique that you use doesn't necessarily mean that it is providing any more proof than something else, or any more quote-unquote proof than something else. It is the design of the study that provides the more causal evidence, not the actual statistical technique that you use after the fact that's providing any sort of statistical evidence that there is something that is going on there. All the regression provides is a relationship between this and that. In order to get better causal evidence, you have to think about what is the design of what you're trying to capture. And that is where you go back to you can look at some of the older videos that I have on this, but basically it's going back to second grade science when you're trying to design a particular experiment You're trying to think about different treatments and controls, and you're trying to estimate those different treatments and controls using that. And that's all I wanted to point out. But, so here's the really cool thing with regression. It is going to become more and more important. There is a lot of techniques that use this, and the reason why it's going to become more and more important, and you all should be very interested in this, is because the world is gathering what's called big data. This is gathering lots and lots of data out there, and we're storing lots and lots of data. And data is just observations of the world. That's it. And we're storing all of these observations in the world, and there's not a really good way to estimate that. The best way to estimate and the different relationships between how the world works is through a regression. And so you might hear about different things like machine learning. The basics of that are basically fundamentally regression of some sort. There's a lot of, you're trying to estimate using best fits of what previous data looks like to sort of project what the future world is going to look like. And that's all you're trying to do, is use some sort of regression technique of to some degree over this large data set, and where as the data gets bigger and as we store more and more data and it becomes more tricky, that technique is we're gonna use more and more of this sort of regression techniques moving forward. They're gonna become more and more important to not only science but also society. So that's all I wanted to talk about today. If you like these videos and you think that they're interesting, make sure you do subscribe. You could do, for this video, you could do an old thumbs up as well. You could do one of those as well. I always like making that sound. That's totally fine with me. You can also go and look at the old videos, watch some of those. If you think what I'm doing with reciprocity, sharing economy, proofreading platform that I'm trying to build, there's two components to that. You can go on there and actually get some of your own work done. But the other component is I'm actually going to be using this for sort of scientific effort. So if you like that, you can look to see what I did, what I'm doing with older videos. So that's it. All I wanted to say is take care, and I'm going to see you on the next video. Bye.